In this video, we are going to briefly mention Green's theorem and then talk about how it relates to the Helmholtz theorem. This is a shorter video, so we'll spend about 3 minutes discussing this overview slide, and then we'll go through each topic in more detail and with more examples. The first thing we are going to do is read through Green's theorem with a couple of comments, but its main function is to help us to prove Helmholtz theorem, which says a vector field, if it exists, is uniquely determined by specifying its divergence and curl everywhere within a region and its normal component on the closed surface surrounding that region. And it's useful, Helmholtz is useful for separating vectors into two parts. One part with zero curl and one part with zero divergence. And through Helmholtz, we say that we can write V, any vector field V, as a del cross A minus the gradient of phi. And we have these two properties, this first one proved in a previous video, that the divergence of del cross A, that's this first part here, is equal to 0, and then the curl of the gradient of phi, that's the second part, is equal to 0. So you can kind of see how we're starting to isolate and separate this out. Finally, we'll do a short discussion about curl or fields that have 0 curl, and then we'll do a discussion about fields that have 0 divergence. And the first thing here is Green's theorem, which this is the second form that we use in the proof, that the surface integral of u times gradient of v is equal to the volume integral of the gradient of v dotted with gradient of u plus u times the Laplacian of v. And really, the main comment I'm going to make about this Green's theorem is this is not the one that I learned in vector calculus. I guess it's a different form based on Gauss. The one I learned in vector calculus was relating the line integral of a boundary of a domain to the surface integral over the domain, and it was based on Stokes. So this is different from what you may recall from vector calculus, and I'm going to say, but that's okay. The main purpose of having Green's theorem here is to prove Helmholtz theorem. And Helmholtz theorem says a vector field, if it exists, is uniquely determined by specifying its divergence and curl everywhere within a region and its normal component on the closed surface surrounding that region. So once you know divergence and you know curl and you know the normal component, you can identify the vector field uniquely. And that point is written here. If we have a vector field we are trying to determine, and we know the value of the divergence and curl at every point in some volume, plus the normal component of the vector field on the surface of that volume, then there's only one vector field that will make all of these, the three conditions work. Second point is this phrase here, if it exists. It's necessary because I can give you a divergence and curl and a normal, and there may be no vector field that satisfies all the three conditions of the particular divergence, the particular curl, and the normal that I give you. So if it exists, it'll be unique, and you can identify the vector field uniquely through a divergence, curl, and normal. And one of the outcomes of Helmholtz is that it's useful for separating vectors into two parts, one part with 0 curl and one part with 0 divergence. In other words, we can have a vector v and we can set it equal to two parts. This first part is the curl of A, where A is some vector potential, minus the divergence of phi, where phi is a scalar potential. And if you recall from an earlier video, we have this identity here, and this one I did not prove for you in another video, but it's one that you should know, so I'll just have this here. I think we discussed this before when we talked about curl. But anyway, the two identities are that the divergence of the curl of A is equal to 0. So over here, this first part of V, this is if you take the divergence of this portion, it'll be 0. And then second, the curl of the gradient of a scalar field is equal to 0. So if you look at this and you take the curl of this portion here, this will equal to 0. So V is a combination of a curl of A, whose divergence is 0, and the gradient of phi, whose curl is 0. Continuing with this idea that V is broken up into one part whose divergence is 0 and another part whose curl is equal to 0, let's go ahead and just take the divergence of the whole vector V. So divergence of V equals divergence, and then I just plug in this expression, curl of A minus gradient of phi. So when I dot this over here, the divergence dot the first part, curl of A, we've already said that equals to 0. When I dot the del with this del over here, the gradient del, we get del squared, or the Laplacian, of phi. Since this goes to 0, we're left with the Laplace of, or negative Laplace of phi. So the divergence of V then is totally dependent only on this phi, which is a scalar potential. So the divergence is specified by the scalar potential phi. I can now take the cross product of my vector V, so that's the cross product of this whole expression, so that's del cross A minus del cross gradient of phi. I guess I've already distributed I need parentheses here. And then, as we saw here, the cross product of a gradient field is equal to 0. So this goes away. So what this tells us is the curl is specified completely by this vector potential A. And finally, we have the norm of V, and that's specified both by the curl and the gradient. So both the A and the phi. For my last topic, I just wanted to talk about vector fields that have 0 divergence and 0 curl, vector fields that have only 0 curl, and vector fields that have only 0 divergence. So first, just a statement that V equals the constant vector field, which I've drawn here, has 0 divergence and 0 curl. And you can do the calculation for the curl to verify that, because you just don't want to get, even straight lines can have curl. But if you set V equal to constant, you'll see the curl is equal to 0. You can see the divergence is equal to 0, or you can calculate and verify. Next, I wanted to draw a vector field where the curl is equal to 0, but there's possibly divergence. So here I have a radial vector field. My V is my radial vector field, so things are radiating out. So you can see there's a source here, and it's definitely diverging, right, because there's a source. But also you can see there's no curl. And I had done an example of a radial vector field, so you can also calculate to verify there's no curl. So something about vector fields with curl equals 0, that's when del cross V equals 0. We have seen in a previous video, if curl is equal to 0, that means we can write V as the gradient of some other scalar potential field. So that means V equals negative del, or gradient, of a scalar potential field. And we also had briefly mentioned before that when curl is equal to, we mentioned when phi is a scalar potential field, we call that a conservative field, which means that the line integral is independent of path. In other words, when you do an integral over a path, you don't actually even need to know the path. You just need to know the endpoints when you do the line integral. Which means if A equals B, in other words, you have a closed path, then a line integral over closed path of a scalar potential field or a conservative field is always equal to 0. So all of these statements, that the curl is 0, V is the gradient, or V has a scalar potential field, the line integral is independent of path, and an integral around a closed curve is equal to 0 are all equivalent. Oh, and I should also mention when a field has 0 curl, we call that irrotational. This last field here is exactly the picture I gave to illustrate curl in a previous video. So we have this little paddle wheel in our vector field, and it kind of gets pushed around in this circle, so it's circulating. That is not curl, that's just circulation. But what is curl is the fact that if we draw an arrow on this paddle wheel, as it circles around, you can see the whole paddle wheel is rotating. So it's the rotation that says that this field has curl. But you can also see it has no source points, so it has zero divergence. And when something has zero divergence, we call it solenoidal. And so some facts about a solenoidal divergence equals zero field. So we have del dotted with V equals zero. From this identity, that means we can express V as the curl of some other field A, where A is a vector potential field. Equivalent to that is the fact if we look at the surface integral, it's going to be independent of the surface if we have divergence equals zero. And so all we need to know to do the surface integral is its boundary. Sort of like over here, when we have a line integral is independent of path, all we need to know are the endpoints. So here when we do the surface integral, all we need to know is its boundary. We don't need to know it's surface independent. And then finally, that means that over a closed boundary, so like what would be a closed boundary? If our boundary is, say, like a closed circle of our surface, then the surface integral will equal to zero. You can see the four equivalents for curl equals zero. That's 1, 2, 3, 4. The four equivalent statements is totally analogous to the four equivalent statements for divergence equals 0, 1, 2, 3, 4, right? They're very parallel. First, we have a scalar potential field. Here we have a vector potential field. We talk about being independent of path. Here we talk about independent of surface. And last, over a closed path, the line integral is 0. Here, over a closed surface, the surface integral is 0. To review what we have discussed in this video, we took a quick, very brief look at Green's theorem, this form of Green's theorem, and the only other thing we talked about Green's theorem is that it's used to prove Helmholtz theorem, which we did not prove, but we talked about its ramifications, which is a vector field, if it exists, is uniquely determined by specifying its divergence and curl everywhere within a region and its normal component on the closed surface surrounding that region. So if we have a vector field we are trying to determine and we know the values of divergence and curl at every point somewhere in the volume, plus we also know the normal component of the vector field on the surface of that volume, then there's only one vector field that will make all of these three things, the divergence, curl, and norm, work. And the qualification, if it exists, is there because it's entirely possible to specify values for divergence, curl, and normal component where no vector field can satisfy these three conditions. And then the last topic was that Helmholtz is useful for separating vectors into two parts, one part with zero curl and one part with zero divergence. So we wrote our vector is equal to the curl of some vector potential field minus the gradient of some scalar potential field. And then we also looked at this what it means for a vector field to have zero curl. That was equivalent to, well, del cross V equals 0. It's also equivalent to saying that V is equal to the gradient of a scalar potential, or it's a scalar potential field, also called a conservative field. And tied in with conservative fields are that line integrals are independent of path. That is, you only need to know the endpoints in order to evaluate the line integral. And if the endpoints are equal, you have a closed path. So the line integral over a closed path is equal to 0. And then we talked about fields that have zero divergence, and zero divergence is equivalent to del dot V equals 0. Actually, that's the definition. And that's equivalent to V is the curl of some vector potential field A. And this is equivalent to saying that if you take the surface integral, it's independent of the surface and only dependent on the boundary. So if you have a closed boundary, then the surface integral over a closed boundary will equal to 0. So that's it for this video. Thank you for watching.